That feeling when you recorded a 30-minute lecture without your microphone on. Here I am to do chapter 5 notes again, and let's hope that the microphone is working. Also, very clear to me that none of you listened to 4.1, 4.2 because there's no sound on that one either. But since that's not as important, I'm going to go back and redo that one later. All right, let's get to it, hopefully. Chapter 5 notes. Oops, you don't need this. All right, so let's take a look at the atomic model. We had some problems with the model that we ended with at the end of chapter 4.2, which of course you didn't listen to because I had no sound and you didn't tell me about that. I'm a little salty. But yeah, so we ended with Rutherford's model, which was like a solar system. Okay. However, the model, he still did not fully explain a lot of the chemical properties of atoms. So we needed a new model, or really we needed a refining of Rutherford's model. So enter Niels Bohr. Boring. All right. He came around and he proposed that electrons could only be found in specific orbits around the nucleus, which is where we ended, like the solar system. However, he added on to this the concept that electrons could only occupy orbits that correspond to a fixed energy. All right. So it requires a certain amount of energy for these electrons to be in these orbits, and they will not leave that orbit unless that energy changes. All right. So electrons can move from one energy level to another, but they have to gain or release energy to do so. Now think of this like a toll booth. You might not be old enough, but you may know that like at some toll booths, you have to put in the exact change. And if you don't put in the exact change, they won't let you go through. Okay. So moving from energy level to energy level is like going through a toll booth with exact change. Okay. You have to put in the exact change to move an electron from energy level 1 to energy level 2, for example. Now, to go further into this concept, okay, the amount of energy that's required to move between different levels isn't the same, but between levels it is fixed. So these are called quantums or quanta of energy. So the amount of energy you need to move from level 1 to level 2 in a given atom is always going to be fixed. All right. One thing that you don't really need to know too much about, but I'm going to just go over really quickly, is that higher energy levels require less energy to move between levels. Now, if you think about this, you can ask yourself why. Now, first of all, this drawing is not first of all, it doesn't look like this. This is just a visual representation. Okay, the solar system model is not actually what actually is happening. But to draw this more accurately, actually these lines further out would be closer together, indicating that it requires less energy to move between these higher energy levels. And so you can ask yourself the question, why might that be? Okay. The answer has to do with the fact that, remember, these energies are related to the attraction between the positive nucleus and the negative electrons. Now, the further away they are, okay, it takes more energy to keep them connected. However, they're so far away from the nucleus, it's easier to move away, further away from the nucleus, because that attraction isn't as strong. You don't need to worry about that too much, but if you move on in chemistry, it's something, just a concept that is good to know. So I just wanted to put that out there for you guys. Okay. I am actually going to go, well, let's do this. Okay. So you've seen these pictures of atomic orbitals. All right. Now, these are the actual shapes of the orbits that electrons occupy. Okay. Electrons don't actually float around the nucleus like circles, like a solar system. They actually occupy orbitals that are these weird shapes. Okay. And some of them get a lot weirder than this, but these are the simple ones. You can look at your book on page 131 for more pictures of what atomic orbitals look like. All right. But there's 4 different types of orbitals. We call them sublevels: S, P, D, and then F, not pictured. Okay. Now, in each specific orbital, electrons will be somewhere in this colored space. Okay. But anywhere where there's white space, the electron cannot be. Now, it's not actually like a physical thing that they're floating around. All right. These orbitals, it's not like inside an atom there's like this circle, and the electron can only go within the circle. Okay, remember the electrons have fixed energies that they have. Now the orbitals are actually solutions to complex mathematical equations about the probability of where an electron will be if it has a specific energy. So it's like, okay, if its energy is this, then it must be in this circle area somewhere. Okay, now you don't need to know that. Like the mathematical problems, I know some of you are in calculus, it's like very complicated multivariable calculus and beyond, but at least you can understand the concept that these are actually mathematical solutions, all right, or a range of mathematical solutions. It's not one solution. Okay, this is where, this dumbbell is where the electron could be based on the amount of energy that it has. Okay, so that's what an orbital is. Now the orbital is kind of like the smallest substructure that we're going to look at in terms of energy levels. But let's take a step back and look at principal energy levels and sublevels. Okay, this is bigger than orbitals. Okay, orbitals is the smallest. Oops, sorry. Okay, so each row in the periodic table generally represents a principal energy level. You go from 1 to 7. So if you take a look at my periodic table here, row 1, 2, 3, 4, 5, 6, 7. All right, that's principal energy level 1, 2, 3, 4, 5, 6, 7. All right, we represent these principal energy levels as N. Okay, so if you look at this picture here, you see how they say N equals 1, N equals 2, N equals 3, N equals 4. All right, those are the principal energy levels that are being discussed there. Okay, now again, as you go down rows and periodic tables, you add energy levels. Energy level 1, 2, 3, 4, 5, 6, 7, all the way across. Okay, now as you go up in energy levels, you add new types of what are called sublevels. So within each energy level, you have different sublevels within that energy level. Think of it as like room types in an apartment, or I don't know. I'm going to go with room types in an apartment building. Okay, so there's 4 different types of sublevels that exist practically in nature. There are more that go beyond this, but like really very, like maybe 100 people in the world care about those, and you are not one of those 100 people, and neither am I. Okay, so the 4 sublevel types are S, P, D, and F. Now, this sentence here, as you go up in energy level, you add new types of sublevels. What that means is energy level 1 only has 1 type of sublevel. Energy level 2 has 2 types. 3 has 3 types. 4 has 4 types. As you go up in principal energy level, as you go down these rows and up in principal energy level, you're adding sublevel types. Now, within each sublevel, you have a certain number of orbitals. Okay, remember, orbitals are these pictures that we drew here. Okay, so within each sublevel, you have a certain number of orbitals. Okay, the S, and these are numbers you just have to memorize, right? And it's easy because it goes up by 2. Well, not easy, but straightforward. Okay, so the S orbital, the S sublevel, you see this vocabulary gets tricky, so you got to be careful about it. The S sublevel always only has 1 orbital in it. The P sublevel always has 3 orbitals. The D always has 5, and the F always has 7 orbitals. Okay, doesn't matter what energy level you're on. If you have a D orbital, if you have a D sublevel, you're going to have 5 D orbitals within that sublevel. Okay, 5 orbitals within that type. D is the type, and then the 5 orbitals are the number you have within that type. And then the last thing you kind of need to know is that every orbital can hold 2 electrons total. All right, which means that the S sublevel, since it only has 1 orbital, will hold 2 electrons total. The P sublevel, because it has 3 orbitals, will hold 6 electrons. 3 times 2 is 6. D will hold 10. 5 times 2 is 10. F will hold 14. 7 times 2 is 14. Right? So let me say this all one more time. So hopefully it's not too confusing. And it should get clearer as this lecture goes on. Like when we're done with the lecture, when you come back to this, it might make more sense to you after we've done electron configurations and all that stuff. Okay? Principal energy level. 1, 2, 3, 4, 5, 6, 7. Just go down the rows. Okay? Within each principal energy level, you have sublevels. S, P, D, or F. However, the number of sublevels you can have depends on what level you are in. So energy level 1 only has 1 sublevel. 2 has 2. 3 has 3. 4 has 4. 5 is 5, but we don't care about the 5th sublevel. Within each sublevel, you have a certain number of orbitals. S sublevel always has 1 orbital. P sublevel always has 3. D sub always has 5. F sub always has 7. And then each orbital can hold 2 electrons total. Taking all that knowledge together, you can calculate how many electrons can fit max in each principal energy level. All right, so let's start with energy level 1. It only has one sublevel, and that is the S sublevel. And so we'll call it 1S because it's energy level 1, the S type. So 1S sublevel. All right. In 1S, you have 1 orbital total. Since each orbital can hold 2 electrons, the maximum number of electrons in principal energy level 1 is 2. Moving on to principal energy level 2, you have 2 sublevels. We have the 2S, just like in 1 we had the 1S, but now we also add a new sublevel, the 2P. Okay, that has 3 orbitals. Okay, because we memorized up here that P has 3 orbitals. Okay, it's right here. Okay, so 2P has 3 orbitals total, which means I have 4 orbitals total in energy level 2, which means the maximum number of electrons is 8. Now we're going to come back to this, but I want you to take a look right here. How many elements are in row 1? There are 2 elements in row 1, and we say that the maximum number of electrons in energy level 1 is 2. There are 1, 2, 3, 4, 5, 6, 7, 8 elements in row 2, and there's 8 maximum number of electrons in row 2. Guess what? I bet you if we count the number of elements in row 3, it will add up to this. It's a little bit trickier, but it will. Trust me. Okay, so energy level 3, we have 3 sublevels, 3S, 3P, but now we add the 3D sublevel. 3D has 5 orbitals, so we have 9 orbitals total, and our maximum number of electrons is 18. And then finally, the 4th sublevel, we add 4F, that has 7, so 4S, 4P, 4D, 4F. Okay, 16 orbitals total, 2 electrons per orbital, 32 electrons total. Now, actually, the maximum number of electrons can be calculated using this equation, 2n squared, where n is the number of the sublevel, n is the number of the principal energy level, so 2n squared. If you take these n's and you plug them into here, you'll see that you get these numbers, all right, and so on and so forth. All right, now we get to the really fun stuff, electron configurations, okay? Electrons are going to arrange themselves around a nucleus inside an atom to make the most stable arrangement possible. All right. It's kind of like, now I told you that closer to the nucleus, it's lower energy. All right. Now imagine if you're filling an apartment building, like which apartments fill up first? The ones with the lowest rent, right? So it's the same concept. Electrons are going to want to play the least amount of rent possible. So they want to stay in the lowest energy levels, sublevels, orbitals, etc. And that is what gives them the most stable arrangement. Okay. Now, electrons arrange themselves into different energy levels and sublevels, and we call those electron configurations. All right. Electron configurations are basically what sublevels are the electrons filling. Okay. Now, they're going to fill in energy levels and sublevels according to 3 rules, which you can find in your book on page 134 and 135, which I would suggest you reread, although I'm going to go over it now. Okay, so we're going to fill in according to 3 rules. All right, and I got to move my face over here for this one. Okay, so rule number 1, Aufbau Principle. Electrons occupy the orbitals of lowest energy first. I'm going to go through the 3 rules, and then I'm going to show you what they look like in practice after. Okay, so Aufbau Principle is electrons occupy the orbitals of lowest energy first. The question you should be asking yourself is, how do I know which orbitals have lowest energy? And we will get to that. Okay, the next one is Pauli exclusion principle. Each orbital holds 2 electrons. I've said that a few times now. What we're adding with the Pauli exclusion principle now is that the 2 electrons will spin in different directions. Now, you're probably used to looking at spin like we did here. Okay, 1 arrow up and 1 arrow down. You can see over here, right? Which is fine. What I want you to know, not necessarily memorize, but at least know and hear, is that we think of spin as up and down, and that makes you naturally think about electrons spinning around either clockwise or counterclockwise around the nucleus. But that's not actually what it is. In reality, it's more like positive and negative solutions to a math problem. Remember, I said these orbitals are complex solutions to math problems, telling you where an electron would be given its energy. Okay, well, there are positive and negative solutions for these math problems, right? It's just like if I tell you x squared equals 4, what's the answer? What is x? You can't tell me x equals 2. You have to tell me x equals 2 or x equals negative 2 because it's the positive and the negative solution. So spin in an orbital, same idea. Okay, it's positive and negative, right? And then the final rule is called Hund's rule. And that says electrons will add 1 electron per orbital in a given sublevel, all with the same spin before pairing electrons. That one is much easier to show rather than tell. So let's get to it. Let's start with Aufbau principle. All right. Your electron configuration gizmo is beautiful, okay? Because it arranges all your subshells by energy. You see here how this is clicked in as energy, right? It arranges the subshells by energy, which means going from the bottom to the top, you go from low energy to high energy. All right. And so the Aufbau principle says we occupy the orbitals of lowest energy first. Well, if you're using the gizmo, you just make sure that before you start filling in a new row, you filled in the row below it. So see 1s2 is filled. Now I don't want to skip to 2p. I want to go to 2s because 2p, you see, is higher. So it's higher energy. I want to fill the lowest energy ones first. So I do 2s first. Okay. Then I go to 2p, right? And then I go to 3s. Okay. So that's what Aufbau principle is. It's going in order. Pauli exclusion. The gizmo does it for you. You're not putting 3 electrons into an orbital and one's arrow up and one's arrow down. Okay. But if you ever see 2 arrows up, you know that that's violating the Pauli exclusion principle. Final rule, Hund's rule. Electrons will add 1 electron per orbital in a given sublevel, all within the same spin before pairing electrons. Okay, now remember, a sublevel is each of these rows. Okay, it's tough to see, but each of these is a sublevel. So 3p is a sublevel, 4s, 4p, 3d. Okay, Hund's rule says I do not do this. 1, 2, 3, 4, 5, 6. Okay, I do not do that. All right, this is violating Hund's rule. Hund's rule says put 1 in each orbital in a sublevel first, then go back and pair them. All right. And then when you pair them, reverse the spin. So the correct way to fill in the 3p sublevel is to go 1, 2, 3, and then come back and fill it in 4, 5, 6. Okay. I'll do that again. Hund's rule says you go 1, 2, 3, fill in 3p, each of the orbitals with 1 electron first, and then 4, 5, 6. Just like, remember the bus? You don't want to sit in the seat next to somebody else. Okay, you want to sit in the seat by yourself before you start pairing up. All right? So I'll show you it with 3D. Same thing. I go 1, 2, 3, 4, 5 across, and then pair 6, 7, 8, 9, 10. Okay? So that's Hund's rule in action. All right. Move my face back. Okay, so electron configurations, writing the actual electron configurations, which is on the worksheet in your problem set 6, okay? The first method, I'm going to give you 3 different methods you can use electron configurations. I would suggest trying all 3 of these methods. If you understand all 3 of these methods, then you understand electron configurations, okay? Obviously, if you have one that you understand really well, just keep using that one. But if you want to make sure you have the deepest understanding of electron configurations, make sure you can do all 3 of these. The reality is all 3 of these is actually doing the same thing, but it's just different visual representations of how to do it, which is why I think if you can understand all 3, it actually just gives you a better understanding overall. All right, method 1 is simple. Use the gizmo. Okay, so let's go back to the gizmo and let's do titanium. You see how I pulled titanium up here? All right, let me show you something about the gizmo. If I give you a problem and it's like, give me the electron configuration of aluminum, just click on aluminum on the periodic table, go back to the electron configuration tab, and then you can do it all out. Okay, and then you can check to see if you have the right answer. All right, that's the beauty of this thing. Okay, but we're not doing aluminum right now, we're doing titanium. Okay, so titanium. first thing I want to do is look at the number of electrons I have. Okay, and you can show the total number of electrons here to make it easier. Okay, the atomic number is 22. You should remember that that means that I have 22 electrons. Okay, now to solve this, I'm just going to use the gizmo. So I'm going to use Aufbau Principle and fill in order from lowest to highest. Okay, now I'm just going to keep filling in until I get to 22 electrons. Okay, so 1, 2, this sublevel is filled, so I go to the next sublevel. 3, 4. See, total number of electrons here is 4. Next sublevel. 5, 6, 7. Notice I'm practicing Hund's rule, filling each box in first before I go back and pair it up, filling in each orbital first before I pair it up. Okay, 8, 9, 10. Still not close, 10 electrons. Go to the next sublevel. 11, 12. Go to the next sublevel. 13, 14, 15. Again, Hund's rule. 16, 17, 18. All right, so I still have 4 to go. Now, the temptation for a lot of people is to move straight to 3D here. But look at what the gizmo has done. It's ordered by energy. And you can see that 4S is lower energy than 3D because it's a little bit lower on the gizmo than 3D. If you're having trouble seeing this on YouTube, just pull up the gizmo. Do it yourself. Okay? It's probably better anyway. All right? So I'm not going to go to 3D yet. I'm going to go to 4S. So I'm going to say 1, 2. I fill up 4S. Now I still have 20 electrons, so I'm missing 2 more. Now I will go to 3D. Okay? 1, 2. Okay? Now I have 22 electrons. The beautiful thing about the gizmo is I can check to see if I have the right answer. And yes, correct electron configuration. I do have the right answer. Now, I do not like how they wrote this. Okay, you see how they wrote 3s2, 3p6. Oh, and let's talk about this. The way you read these electron configurations out loud is you don't say 1s squared. Okay, this number is not an exponent. This is the number of electrons in that given subshell. So the way you read this out loud is 1s2, 2s2, 2p6, 3s2, 3p6. Okay, now I don't like how they wrote this here because they go 3D2 and then 4S2. I prefer if you check this configuration in order of subshell filling, because this reminds me that I filled 4S2 in first and then I went to fill in the 3D. Okay, so that's how you use the gizmo to figure out the electron configuration. All right, so we did it for titanium. All right, so that's method 1. Method 2 is what's called the reverse diagonal method. What you do for the reverse diagonal method is you take a piece of paper and you write out all your sublevels. Okay, so I wrote them out here. 1s2. Why is there not a 1p6? Because you have the same number of sublevels as your principal energy level. Okay, principal energy level 1 only has one sublevel, and that's the S. All right, anyway, 1s2, 2s2, 2p6, 3s2, blah, blah, blah. I write them all out. Okay. And then what you do is you draw arrows in what's called a reverse diagonal diagram. And you draw them in like this. 1s2. You see these arrows coming here. They're going from right to left. Top right to bottom left. And they're filling in and they're cutting through all these sublevels. Now what this actually is giving you is it is telling you the order in which these sublevels fill. And you'll see it gives you the same exact order as the gizmo gives you because the gizmo is correct and this reverse diagonal is correct as well. So like when I was a kid, my chemistry teacher made me memorize this because we didn't have gizmos. All right, 1s2, then 2s2, and I just keep going back and restarting the arrow. 2p6, 3s2, then I come back around here, 3p6, 4s2, right? Come back around, 3d10, 4p6, 5s2, come back around, 4d10, 5p6, 6s2, come back around. All right, so you just keep going around and around, reverse diagonal, all right, to figure out which ones you're filling in order. Okay, now the beauty of this method is we're gonna do titanium again, so we already know the answer, all right, but I'm gonna show you how to use this method to get the answer. Okay, so I have my handy dandy diagram here. Okay, you can look this up online if you can't find it yourself. All right. So I have 22 electrons, so I just want to get to 22 electrons. So what I'm going to do is I'm going to count through here until I get to 22. So 1s2, 2s2, 2p6. And actually the easiest way to do it is this. Take a look at your diagram and just count the numbers until you get to the number you want. So 2, 4, plus 6 is 10, 12, 18, 20. Okay. And then I know that I'm going to end in 3D because 22 will end somewhere in 3D. Once you've done that, all you do is just write it out. You just follow along with the diagram. 1s2, right here. 2s2, right here. 2p6, right here. 3s2, 3p6, 4s2. And then I just make sure I add up to 22 total. 3d2 gets me to 22. And so I'm done. And notice it's the same exact electron configuration we got here. All right. So that is the reverse diagonal method. And again, the gizmo is the easiest, but understanding the reverse diagonal is going to be helpful. All right. Finally, the final method is method 3, periodic table blocks. All right. So take a look at this periodic table. All right. This is colored in periodic table. How wide are each of the selections below? And does it remind you of anything? Okay. Take a look at that and take a look at the reverse diagonal diagram that I drew over here. Hopefully you're seeing that. Take a look at this purple, all these purples, it's 2 across, 2, 2, 2, 2, 2, 2. Just like here, we have 1s2, 2s2, 3s2, 4s2, 5s2, 6s2, 7s2. Now let's go to p's. 6, 1, 2, 3, 4, 5, 6, 6, 6, 6, 6, 6, 6, 6, 6. Ooh, Satan, bad. But anyway, 2p6, 3p6, 4p6, 5p6, 6p6, 7p6. All right. The pattern is full. All right. The pattern is emerging. 3D, well, 3D10. Let's take a look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hello. Still holding up. 4F14. I guarantee you, count across, it's going to be 14. Okay. So what you should be realizing is the periodic table is actually organized according to these sublevels. Or we should say it more accurately, the sublevels exist in real life. And so then the periodic table just fell into place with these same patterns that the sublevels showed us, which should give you an idea of how they figured this out in the first place, right? They went with the data and the data showed them the patterns, and then the patterns were obvious. Okay, maybe not to you or me, but if you study the stuff long enough, they're obvious. And hopefully you can see this pattern here, right? 2, 2, P6, all these P blocks are 6. We call them blocks, right? So we call this green the P block, this purple we call the S block, the red I call the D block, the blue down here I call the F block, okay? Now you can use this concept, this periodic table block concept, to also help you figure out the electron configuration. All right? The way you do it, let's look at titanium again, 22 electrons. Now I'm just going to count, okay, again, or titanium is here on the periodic table, right here. If you don't believe me, we'll come back here. It's right there on the periodic table, okay, which is right about here, okay? So then what we do is we just go across the blocks and count as we go. And the blocks are actually in order. So we just go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, 1, 2, because we stopped here, right? So we only have two of these done, so it's 3d2, right? This next one is 3d3, 3d4, 3d5, 3d6, 7, 8, 9, 10, right? But we care about titanium, which is 3d2. So again, we're going to get the exact same electron configuration that we got in the other two methods, okay? Now, this block method is really helpful for people who are visual learners, because if you just have this diagram out, and you can find this picture online, if you have trouble finding it, just let me know, but you should be able to find it, all right? And then you can just use this to help you to figure out your electron configurations. All right. So we got the same electron configuration 3 times with titanium. You know, I showed you how to do it. Okay. Again, ideally, you know how to do all 3. All right. That will help you to show the most understanding. All right. One thing I forgot to show you really quickly is that you can actually use this gizmo to do the reverse diagonal method. Remember, I keep touting how awesome gizmos are because it's organizing the subshell by energy. However, you can organize them by number. If you do, you can see, you could just imagine the reverse diagonals here, All right, so you can still practice this way, but check your answer. All right, that's not super important, but just in case you need that. All right, we're almost done. We've got to finish up with noble gas configurations. I know a lot of you like to take shortcuts. Okay, I'll tell you right now, this is a good shortcut, but if you screw it up, you get the whole thing wrong. So make sure you know how to do it the long way before you start messing around with this. Okay, so noble gases represent the complete filling of the s and p orbitals of a given principal energy level. They are among the most stable compounds. All right, the noble gases are the white ones here in this periodic table. I don't know, kind of have a problem with that, but this is the table I've pulled, so that's what we got. All right, so they're among the most stable compounds. All right, now for reasons that will become clear later, noble gases and only noble gases, and when I mean later, I mean like in a week or two, not today. All right, you can only use noble gases for an electron configuration shorthand. Okay, so let's take a look at an example. Neon is here, then sodium is here, and silicon is here. Okay, neon's here, sodium is here, and silicon is here. Okay, neon's electron configuration is 1s2, 2s2, 2p6. Sodium is 1s2, 2s2, 2p6, 3s1. Silicon is 1s2, 2s2, 2p6, 3s2, 3p2. You're just going to have to trust me on that one or check my work yourself. Okay, for noble gas configurations, what you do is you put the noble gas in the principal level below, energy level wise below. So it's actually, it's confusing. You know what? Let me write this in here. Okay, it's in the principal energy level below, but the row above. Okay, it sounds confusing, but hopefully you're getting an understanding of this. Like the row above the row that you're in is a lower energy. So on the periodic table, the lowest energy is at the top. So it's the row above, but the row above is lower energy. So that's why I say it like this. Okay, put the noble gas in the principal level below, which is actually the row above on the periodic table, in brackets, and then you just complete it. All right, so let's go with sodium. Sodium is here. What's the noble gas in the row below? Okay, or the row above, energy level below. It's neon. All right, remember, all these purple ones are the noble gases. You cannot use any other elements to do this. So neon is before sodium. All right, so what I do is I just put neon's symbol in brackets and then 3s1. It's just like math. It's almost like you're factoring it out. 1s2, 2s2, 2p6. I just take that and I turn that into neon. Neon 3s1. For silicon, I can do the same thing. 1s2, 2s2, 2p6 is the same as neon, so I do neon 3s2, 3p2. Okay, I'm going to reiterate this. There cannot be any symbol in those brackets that is not a noble gas. If you do that, it will be wrong. It will be completely wrong. No partial credit. Okay, do not put any element that is not a noble gas in those brackets. All right. Now, on problems, if I don't specify, you can either use the longhand or the noble gas configuration. But like I just said, if it's wrong, it's wrong. Right? I think it's good to make sure you're comfortable with using either longhand or noble gas, but you know, it's gonna be up to you. All right, so I've done this 30-minute lecture twice now. Hopefully the audio has come through. If you have any questions, email me. You know how to find me. This chapter is going to be the building blocks for the next 3 or 4 chapters, 6, 7, 8, 9. Okay, so you really need to understand how to make these electron configurations, and you really should understand the concepts of how these electron configurations, you know, form and how we fill in these sublevels. All right, and you really got to know principal energy level, sublevel, orbital. Like how am I, you know, like how am I differentiating between all those things? Okay, it is an organizational difficulty, but it is something that will not only help you for this class, but being able to organize things like that is, you know, it's going to be important for you in your life. Like organizing things is important. All right. So that's a noble gas down there. So, you know, make sure you rewatch this however many times you need to. Find other YouTube videos if mine was useless. Okay. Find those resources out there. This is material that The only way to learn it is to really keep banging your head against it until you learn it. All right. Obviously, I'm around to help, but there's only so much help I can give you. Like, there's only so many ways that I can rephrase things. So you're going to have to utilize whatever resources you can find to understand it better yourself. All right. I'm going to stop this video. I'm going to pray that the audio came through this time. I'm going to post it to YouTube. Let's see. Anyway, good luck, everybody, with all your work.